Okay, guys, so I'll make a start there. Right, so, okay, guys, settle down. Okay, so right at the beginning, the first lecture in this unit, I briefly went over some preliminaries and about PDEs, and I mentioned there are 3 types. Okay, just to refresh your memory, there are elliptic PDEs, parabolic, and hyperbolic. Now, those 3 different types of PDEs have different types of solutions. Okay, so the first one we're going to be looking at is the elliptic PDE. Some of the solution methods I talk about today will also apply to parabolic and hyperbolic. So just because I'm saying, okay, I'm solving this elliptic PDE using this method, doesn't mean it doesn't apply to other methods. Okay. So, yeah, elliptic PDEs is on page 23 of your notes. Okay, so elliptic PDEs model what we call a steady state problem. What that means is the solution to the PDE does not depend upon time. Okay, so the solution does not change over time. It doesn't move, it doesn't evolve, it's a steady state. Okay, so that's the first thing. So that makes solving elliptic PDEs easier than parabolic or hyperbolic, which may depend upon time. Okay, so elliptic PDEs model steady state problems. Solution doesn't change over time. So therefore, time is not a dependent variable. Sorry, time is not an independent variable of an elliptic PDE. So the independent variables of elliptic PDEs tend to be spatial coordinates. Okay, so we have some form of spatial domain, usually x and y, or could also include z, if you go that far. So we have some form of domain. We can solve the elliptic PDE over that domain, and the solution, when we get the solution, that'll be a constant solution, so it doesn't change. The solution to elliptic PDEs are smooth. So by smooth, I mean there's no abrupt changes in the gradients and there's no discontinuities. Okay, so the solution should be smooth everywhere for an elliptic PDE. An example of these, the simplest elliptic PDE is Laplace's equation. Okay, very simple. We have a double derivative with respect to the x variable plus a double derivative with respect to y variable, and that's all equal to 0. Okay, so that equation props up a hell of a lot in electrical engineering, magnetic fields, that sort of thing. There's also what's called the Laplacian. So if you ever go on to do vector calculus, a Laplacian is based upon these double derivatives here. Okay, so if you want to check that out, by all means do a search for it if you want. That's named after Laplace. Poisson came along a bit later and stuck a function on the right-hand side and called it his equation. Okay, so the only difference between Laplace's equation and Poisson's equation is instead of having the sum of the double derivatives equal to 0, Poisson said it must, in his equation, it must adhere to some function f, x, y. Whatever that function is, depends upon what you're modeling. And as it says at the bottom there, these both tend to be used to model electric, magnetic fields, gravitational fields, that sort of thing. Okay, so elliptic PDEs, essentially steady state, don't depend upon time, they do depend upon space. Okay, so if we have 2 spatial coordinates, we have an x domain and a y domain. Okay, so we have a 2D, what we call a 2D domain. We saw previously last week that discretizing a one-dimensional domain was quite simple. We had our delta x. Okay, we had some start value for x, some end value for x, and we filled in 2D domain, we simply extend that upwards. Okay, so here I've got a domain, x extends in the horizontal direction, y in the vertical direction, and this grey rectangle, that's our domain. Okay, the x domain starts at A, so that's a lower bound, and extends upwards to B. And I've labelled the y domain starting at C, extending up to D. Okay, these are just arbitrary, whatever they are. They're just arbitrary. Okay, so that's our domain. Right, so in discretizing it using a finite difference method, we form what we call a finite difference grid. So if you cast your mind back to last week, we just had the X line, we just had the X domain, and we put a node at the smallest value of X, which is A. We put a node at the largest value of X, which is B, and we filled some discrete points between those. Okay, so that was what we did last time. This time we have a 2D, so we extend it upwards, and we have this, what we call a grid or a mesh. You tend to refer to grid and mesh interchangeably, but strictly speaking, this is a grid. The reason being is these the X direction and the Y direction are perpendicular to each other. Okay, it has to be a grid. When we use finite differences, we have to have that square grid configuration. Next term, when you look at finite volume, you'll see where we can use a mesh, where we don't necessarily have to have a square configuration of our points. Okay, so each of these points represents a finite difference node, and it represents a point where we're going to solve our PDE. Okay, so for each point there, you can see, whereas before we might have just had something like 7 nodes along one direction, here we've got 7 times 5, so we've got 35 nodes. So you start, when you go into the second dimension, you start to sort of significantly increase the number of nodes you have. Okay, and the step lengths in the X and Y direction are usually labeled delta X or delta Y respectively. Okay, so that's discretizing our 2D domain. Okay, as before, okay, so if we had our X domain is in the range A to B, and our Y domain is in the range C to D, and we have nx plus 1 and ny plus 1 nodes in the X and Y directions, then we can calculate delta X and delta Y like this. Okay, so this is exactly the same as what we saw last week. If you had the number of nodes nx and ny, you could obviously interchange those to give the if you had the delta X and delta Y, and you needed to calculate nx and ny, you can do that by interchanging them. Okay, just 1 second. Sorry about that. Okay, so with that, we can also calculate the coordinates of nodes. So X coordinates are calculated as before. This time the Y coordinates are calculated by adding J times delta Y. Okay, so the convention I'm going to use is that in the X direction, I'm going to call my index I. Okay, so the first node in from the left, I would be 1, second node in, I would be 2, etc. So across, I use a convention of I. When I go up, I'm going to use the convention J. Okay, so J times delta Y. You've got to be careful here a bit, because when we talk about matrices, you normally think of IJ matrix, where I is number of rows, J is number of columns. This has been interchanged. Okay, so you try not to get confused by that. The reason I've chosen I and J in this way round is because that's what's most common in textbooks and the literature. Okay, so there's what I mean by a finite difference grid. This is for the middle node, is what I refer to node U and in subscript IJ. Okay, so whenever we're considering the solution of a node, we say, okay, that's our node IJ, that's the middle one. Surrounding node IJ, there are 8 other nodes, and we use the IJ notation. So this one in the bottom left, we step 1 node to the left, 1 node down, so we have I subscript I minus 1, J minus 1. And you can see the way all the other nodes fit into that. Okay, so just remember, I goes across, I is our index to going across the X direction, J is our index going up the Y direction. Okay. Are there any sort of questions on that? Is it all okay so far? Yeah, no nods, no. Okay, do shout out if there's anything you don't quite understand. Okay. Right, so that's the first thing we're going to cover, discretizing our domain. So that's how we split up the domain into those discrete finite difference nodes and how we solve it. In the example which we looked at last week, we introduced the idea of a boundary node. Okay, so just to refresh your memory, we may have a node on the boundary. And if you recall, finite differences or finite difference approximations use nodes quite often either side to calculate a derivative at that node. But of course, if we try to use a node to the left outside the boundary here, we don't have a node there. So to overcome that problem, what we can do is we can say, okay, the boundary node is going to be exempt from any calculation, and we're going to calculate all the nodes which are inside the domain, which I've labeled computational nodes here. Okay, this will depend upon whatever finite difference scheme you use. Okay, sometimes that might not be necessary. Sometimes it will, it just depends. So the boundary nodes are omitted from the finite difference scheme and assume some value. Okay, the value that these boundary nodes assume are what we call boundary conditions. Now these are based upon what sort of behavior do we want at the boundary. Okay, remember, but quite often when we're solving PDEs, it's because we're modeling some physical phenomenon. Okay, so if you're modeling something, you say, okay, at the boundary of our domain, I want this behavior to be modeled. So therefore, that will dictate what the values of your boundary nodes are. There are a few types of boundary conditions. In this unit, we're just going to be looking at two types. They're called Dirichlet boundary conditions and Neumann boundary conditions. Oops. Okay, so the first type is Dirichlet boundary conditions. This is the simplest type, and this is used when the points on the boundary are not influenced by whatever's going on inside the boundary. So they're independent upon the behavior of the system within that domain. Okay, so they're not influenced by whatever's going on. So the values could be constant. Now, last week we used constant values of 0. So if u0 and un are my boundary nodes, you could set them, okay, they're always going to be equal to 0. Whatever happens within the solution, within the computational nodes, with Dirichlet boundary conditions, we could say, okay, they're always going to be equal to 0. Okay, totally independent of the solution. Or we may want the values of the boundary to adhere to some function. It depends. I mean, you may have some outside influence on your domain which you want to model. And in that case, you set the boundary nodes to some function. Okay. You may notice I've got t here. And I said before, well, hang on, elliptic PDEs don't use t. Well, you could also use Dirichlet boundary conditions with parabolic and hyperbolic. So that's why, in case you're wondering why I've put t here. Okay, this is more of a general case. If it was an elliptic PDE, I wouldn't have that t. It would just be a function of x and y. So that's when the boundary can adhere to some kind of function. For example, let's say we're modeling water. Okay, and then from one side of the domain, you want a wave to be produced. So you can say, okay, give me a sinusoidal wave function. Okay, so that boundary, maybe you have an oscillating function, and then that will influence the nodes within the boundary. Okay. And the final one is quite a nice one. It's periodic behavior. Okay, so if you want behavior within the domain to be repeated, we can use a periodic boundary. Now, what this does, it sort of wraps around. So imagine you're modeling, I don't know, some flow of energy out through a system or something, or along a channel or a bar. When something happens on the right-hand side of your domain, what happens then is you want that to be replicated at the left-hand side. So do you remember the Pac-Man games? The Pac-Man game had a maze, and you can escape through the right-hand side of the maze, and you'd appear at the left-hand side. So as you go down through the right-hand door, you'd appear in the left-hand door. That's what we mean by this periodic behavior. So we can model this by, we set the left-hand boundary node equals to the last computational node. So this node here takes on the same value as that last computational node. Okay, so therefore, this U1 that takes its this U0 influences. Okay, this can assume that it's at the other end. So it models an infinite domain. And you could do things the other way around. The right-hand boundary could take this value here. So the first computational node, that's where the right-hand boundary takes. That's another example. So we could use periodic behavior. Okay. In short, Dirichlet boundary conditions, they're independent on what's going on inside the domain, and we can set them pretty much to what we want. Okay, the other type was Neumann, and these are when the values on the boundaries are influenced by the values within the domain. So if something happens within your domain, it's going to have an effect on the boundary node. And this usually has an effect of a derivative across a boundary. Okay, so values, the second bullet point there, the values of the boundary nodes are determined by evaluating derivatives across the boundary. So if you look at this diagram, okay, we've got a similar diagram from before, but this time on the boundary, I have my boundary node. Okay, if I want to calculate a derivative across that node, I'm going to need some information from outside the domain. Okay. Before I said, well, I'm just going to use Dirichlet boundary conditions. But in this case, I can't. Dirichlet boundary conditions are no good because whatever's going on for this node, we're going to have an effect on that node there. Okay. So what we do is we invent a node and we call it a ghost node. Okay. So this node, which exists somewhere outside of our domain, this is called a ghost node. Okay, I've labeled it U-1 here, okay, just to keep going. And at the other end as well, UN+1 is the other ghost node. Okay, the value of this ghost node is what we calculate. Okay, this value here is included in the computation in the finite difference scheme. This is the value which we then calculate using these values. Okay, so that's Neumann conditions. That's when you have some derivative, some gradient which exists across the domain, across the boundary of the domain. Right. Okay, so I'm going to talk in general terms to start with. So let's say we have a first order derivative across our boundary equals to some function f of u. Okay, so we have a first order derivative. We can approximate that using finite difference, central difference, second order central difference. Okay, so across the boundary, so remember we're looking at the derivative across the U0 node. Okay, so if I go back one, we're looking for what's the derivative across this node here. So using the central difference formula, okay, we have the node to the right minus the node to the left divided by 2 times the step length. That's going to be equal to my f of u. Okay, because I want the gradient to be equal to that f of u. Okay, rearrange to make the ghost node the subject. Okay, so you have the ghost node is equal to the second computational node. So this is the second one in from the boundary. Well, the one adjacent to the boundary node, minus 2 times step length times whatever that function is. Okay, normally that function's 0. Quite often we want what we call a transmissive boundary. This is a boundary where it allows any flow to escape through the domain without hindrance. So if we're modeling water and you use the transmissive boundary, what will happen is any waves will just flow out the boundary as if it wasn't there. Okay, so if you set f of u to be 0, you simply got this one there. And I think of that, I don't know what's going on there, but if we concentrate on the left-hand boundary, the ghost node will equal that node U1. So if we just go back a sec. Okay, this node, if I want a transmissive boundary at this boundary condition, this node takes on the same value of whatever that node is, which makes sense. If I want this gradient to be 0, and these two have the same value, that's just going to be flat. Okay. Another handy application of Neumann boundary conditions is if we want solid boundaries. Let's say we're modeling something where any movement or motion or energy within the system is contained within that system and it's not allowed to escape. We have a solid boundary. Like consider a tank of water, like a fish tank. Okay, those walls which hold in the water don't let any water flow out through them. Okay, We can model this by if v is a velocity, okay, it's a dependent variable, it's some velocity. If v of the ghost node is equal to minus v of the computational node, what that means is there's absolutely no way that any flow can go through the boundary. We'll revisit this boundary condition when we look at systems of PDEs, and that was about week 10 of this term. Okay, so those are boundary conditions. Dirichlet, which are constant, they're what's going on in the domain has no bearing on the boundary, and we have Neumann, where what's going on in the domain does have a bearing. Okay. Right, so we now know how to discretize our 2D domain. We know about boundary conditions, so let's go ahead and form our finite difference scheme. Okay, so in this chapter, I'm going to use the Laplace equation as an example. It can also be applied to any other elliptic, and also some other parabolic and hyperbolic equations. Okay, so this is just sort of a general method. Okay, so I've got two second-order derivatives. So what I do is, if you look at the toolkit, I have to approximate those double derivatives. So I'm going to use second-order symmetric differences. Okay, I could have used higher order, I could use third or fourth order if I wanted to, but for this example, I'm just going to use second order. Okay, so I replace the double derivative uxx with our second order symmetric difference. And so if you recall, it's the node to the left minus 2 lots of the node in the center plus the node to the right divided by the step length squared. And I also do that the same for the y. Okay, so that's exactly the same, except for we're going node beneath minus 2 lots of the center node plus the node on top. Okay, so remember the I minus 1, I, and I plus 1, that goes horizontally, and the j's, when the j's change, they go vertically. Okay, so I replaced a differential equation with an algebraic equation. Okay. If I rearrange this to make uij the subject, that's the center node. That's the node which we're trying to solve for. So do a bit of algebra and we get to this. Okay, that's fine. That's our general form of the finite difference scheme. I can simplify that a bit by if I say, well, I'm going to let my step length in the x direction be the same as the step length in the y direction. Now, we don't have to do this. The only reason I'm doing it is to make the calculations easy. But next week, when you come to do the lab sheet exercises, you'll see we'll have different values for delta x and delta y. But for this example, I'm going to say, okay, I'm assuming I'm going to let delta x equal delta y. If that's the case, this simplifies down to this. All we have here is the average of the adjacent nodes in the compass direction. Okay, so we have the node on top, plus the node to the right, plus the node on the bottom, plus the node to the left, all divided by 4. So it's essentially the average of the 4 compass nodes. That's our finite difference scheme. Okay, that's an approximation of our solution at node ij. Okay, so last week I introduced the idea of a stencil. So here's a reduced stencil. So it's sometimes useful to actually draw these out. Okay, so that's the middle node, and we've got the node to the left, right, top, and bottom. And the convention is we draw a line indicating which nodes are affected by which other nodes. Okay. Some people prefer to use compass notation. UO is the original node, which is the one you're trying to solve for, and then you have north, east, south, and west, all divided by 4. So it's quite a simple scheme. Okay, probably the simplest one you can come across, really. Okay, so that's our finite difference scheme. Exactly the same as what we did last week. Replace your derivatives with finite difference approximations, do a bit of algebra, and rearrange for the node ij. Is everyone okay up to now with that step? Okay, so now what we're going to do now is I'm going to look at how do we compute that node using that scheme. And I'm going to do it over quite a simplified grid. Okay, what I've got here is I've got a 2D domain, and I've chosen 5 nodes in the x direction and 4 nodes in the y direction. Okay, and notice the numbering convention. So we tend to start at 0. So this is node 0, 0. As we go to the left, our I increases. So we go, no, remember it's node ij. As we go to the left, we have 1, 0, 2, 0, etc. As we go up, it's the j that increases. This can be confusing, especially when you consider matrix notation. Matrix notation is when the I and j are flipped. Okay, so try not to get confused with that. Okay, so we tend to use the first number to mean what node is it across, and the second number to mean what node is it up. Okay, so that's what I'm going to solve for. The white nodes are my boundary nodes. Okay, I'm going to use Dirichlet boundary conditions here. The dark nodes are the ones which I'm going to solve for. So I'm only solving for those 6 in the middle. Okay. And here I'm going to use these initial and boundary conditions. Okay, so the nodes in the middle, the ones I'm going to solve for, I'm starting them all off at 0. It doesn't matter what I start them off at, because you remember elliptic equations are steady state solutions. I could start these off at any number I can think of, all of them different. The solution will still be the same. Okay, the solution to an elliptic equation is not influenced by its initial conditions. Okay, so it doesn't matter what you start with. I just always tend to start at 0. Makes sense, really. These numbers on the outside are just numbers I've made up. They don't mean anything. They don't model anything. I just made them up. Okay, so these are always going to have, for example, this node is always going to be 8.4. Okay, no matter what happens within the domain, this node is constant 8.4. And in fact, I'm not even going to bother ever changing the value of this node. Okay, so that's our problem. That's our initial and boundary conditions. What I'm going to do now is just show you what nodes are affected by what other nodes. So if I was to look at this node here, which is node 1, 1, this is my first computational node. Okay. So to calculate the value of this node, we take the value of the node on top, which is U12, plus the value of the node to the right, which is U21, plus the value of the node to the bottom, which that's always going to be 6.8. So I can write that there. And the node to the left, that's always going to be 7.2. The boundary conditions. The boundary conditions. I mean, is that what you mean? Have I chosen them randomly, or? Yes. I haven't, not necessarily randomly. I just made them up. Okay. I just needed some numbers to go in there, so I made them up. If you wanted to model something, that's when you consider, okay, what do I want those nodes on the boundary to be? For example, if you're modeling temperature, you might want the node on the boundary to be 0 if something's freezing outside. That could be an example, but for this example, I just made them up. Okay, so that's the first node. If I move, what we tend to do is a row by column order. What this means is I start on the first row, and I do all the columns across. So I'm going to start on this node, and then I'm going to go to the node to the right next. Okay. So the next node along. Okay. In this case, we've got a few unknowns. Okay. So the node to the north, the east, and the west, I don't know what that solution is. Okay. Eventually, I will know what the solution is, but for now, I don't. So these are unknown values. The only node I know the value of is this 7.7 below. Okay. And if we go across again, this time I've got 2 known values, which are the node to the east and to the south. The other 2, which are the north and west, I don't know what the value are. So notice the nodes which I'm solving for, i.e. the 6 in the middle, I don't know what their solution is yet. Their solution depends upon the solution of all the other nodes. Okay, so I don't know what they are. So they're unknown values. If I go on the top row, okay, again, we know the value to the north. We don't know the value to the west. We don't know the value to the south, but we do know the value to the to the west. We don't know the value to the east. Okay, and if we keep going in that vein, okay, this is what we have. We have 6 equations. We have 6 nodes which we want to solve for. We have 6 equations. So you might sort of start to guess where I'm going with this. Okay, so that's what we have, and we can write that as a linear system. Okay, I'm just going to just go back a sec. Okay, all I'm doing by writing it as a linear system is rearranging all these equations so that the unknowns are on the left of an equal sign, and the values I know the value of are on the right. Okay, so I have a system, a linear system of 6 equations in 6 unknowns. Okay, you know how to solve this. You did it in the first year. Okay, you can write it as this matrix equation down here. Use Gaussian elimination. Use matrix inversion if you want. Brilliant, jobs are good. The problem is, in this example, I've only got 6 computational nodes. Usually we got thousands. When we're doing this in real life, we've got thousands, maybe tens or 100,000 nodes. We can't possibly do that using standard linear algebra techniques. Okay, so the only way really we can do this is by using what we call indirect solution methods. Okay, and that's what we're going to talk about for the rest of today and also next week. Okay, so we want to find the solution. The solution, which is this vector here, would give us the values of those nodes. Okay, so that's what we now need to do. Okay, and we're going to look at 4 indirect solution methods. We're only going to look at 1 today. Okay, the other 3 we're going to look at next week. And the first one we're going to look at is called the Jacobi method. And it's an indirect method. A direct method means we just rearrange the equations and solve as per normal using algebraic techniques. An indirect method is what we call an iterative method. What we do is we calculate an estimate of the solution, and then we keep improving on our estimate until we get a pretty good, or what we think is a pretty good solution. Okay, so we start off with some estimate, and we improve until 2 successive iterations agree to a required accuracy. We don't ever get the exact solution using an indirect method. It's an estimate of the solution, but it's a very good estimate. The more we iterate, the more we improve, the better our solution is. Okay, now Jacobi method is the simplest indirect method. What we do is I'm going to let the superscript k in this one here denote the current estimate. Okay, so we tend to use superscript k. That's not a power. That's just say, okay, I'm on this. When k is 0, that's my initial condition. When k is 1, that's my first estimate. K is 2, that's my second estimate. Okay, k plus 1 in the superscript means, okay, this is how I'm improving on that estimate. Okay, so all we do for Jacobi's method is we take our finite difference scheme. I won't go back. We take our finite difference scheme and we calculate the value of uij for the next iteration, or for the improved estimate, is simply our scheme using the current values. Okay, so it's a very straightforward. We've hardly done anything to our scheme, and that will give us our next solution. Okay, so let's step through the example. Using row by column order again, so I'm going across the row and then up. Okay, so the U11, initial conditions were 0s apart from at the boundary. Okay, so our first value, or our first estimate for the solution, 0 plus 0 plus 6.8 plus 7.2 divided by 4, and you get 3.5. Okay. Move to the next node. Okay, what we have here is 0 plus 0 plus 7.7 plus 0 divided by 4, 1.925. Okay, carry on in the same way. Okay, so that's that one there. Okay. Moving up a row. So yeah, moving to the second row. Okay, and across. I'm not going to go through each one of those, but you can see where it comes from, hopefully. So all of these there are now my first estimates of the solution. Okay, let's do that again. Okay, so my first estimates of the solution. Okay, what I've done here on this diagram on the right is I've filled in what our first estimates are. So for example, 3.5 there, that's now 3.5. Okay, so do it again. So the node to the north plus the node to the east, the node to the south plus the node to the west. Okay, so now we've gone from a value of 3.5 to our improved estimate of 5.0625. Okay, do the same with the second node, third node, and we keep going on in that way. Okay, so if I go back to the previous slide, those are my first estimates. These are my second estimates. Hopefully, they're closer to the real solution than my first estimate. So that's what we want. We want to converge. We want to hone in on the actual solution. How do we know when to stop? Okay. The problem we got here is if I can keep improving the solution, if I go forever, I'll get the exact solution. But we can't go forever. Obviously, it's not practical. You've only got a limited time. There's more to life than sort of iterating to extreme accuracy. So we need some criterion where we stop. And this is what we refer to as convergence criteria. And what we say is we'll stop when two successive iterations agree, or the values of those two successive iterations agree to a predetermined accuracy. Okay. But we have a problem. It's all right if we've got one value. Okay, if we keep improving on one value, when two successive values of that single value get very close to each other, we stop. But in our problem, we got 6. Okay, we got these 6 values. So what we need is a way to say, okay, how similar are all of these values to the previous estimates? And the method we tend to use is what we call the L2 norm, or a vector norm. You've seen vector norms before. The magnitude of a vector is an example of a vector norm. Okay, it's a single value which gives some form of measure of perhaps the size of your vector. So, for example, the Euclidean norm, what you do is you square each value, add them all up, and that should be a square root there, by the way. Okay, that there should be a square root. Hopefully, in your notes, it's down as a square root. Bottom of page 30, yeah. About that. Okay, this is what we call the L2 norm. Okay, and vector norm is denoted by that's vertical bars either side of the vector x. In our case, we kind of got a matrix. If we go back a slide, we kind of got a matrix. We can say that, well, that could be a 2 by 3 matrix. All we do is string it out as a vector. Okay, so just square each one of the computational nodes, or calculate the difference between each computational node and its previous estimate, square it, add them all together, square root it, and you've got the norm. Okay, so what we say is if UK plus 1 is the improved estimate and the previous estimate was UK, okay, if we calculate the difference between those two, calculate the norm, that will give us a single number. And when that number's small, we can say, well, our estimates kind of agree with the actual solution, which is U. And what we tend to do is use some form of tolerance, and the shorthand is TOL. This TOL is some small number. Could be a millionth, could be a billionth, something very small. Smaller the number, the closer we get to the actual solution. But we could be talking absolute fractions of like the 10th decimal place or something. So usually TOL is set around maybe 1 in 10,000 or 1 in a million. That's what I tend to use. Okay, so we can actually calculate the vector norm, or the L2 norm, for our solutions. Okay, so the first estimate we had is U1. U0 is the starting value. So this is the initial conditions. These are all 0. So the norm of U1 minus U0 is, okay, so for example, this node was 3.5 and the previous value was 0. We subtract them and square them. If we do the same for all the other 5 nodes, add them all together, find the square root, we'll calculate and we get it 8.9757. Okay, if U2 apart from being a very rubbish band. If U2 are the second estimate minus the first estimate, calculate the L2 norm, we get 4.745. So our norm is kind of like, we want that to get very, very small. So it's got smaller from the first to the second estimate. It will get smaller still. We need that to get really, really small, less than some small value, which we call toll, and that's when we stop. Okay, this is a flowchart. I did draw one of these up for the last week's lecture, but I didn't include it in the slides. Okay, this is the flowchart. This is what we do, how we calculate the solution using an indirect method. Okay, you're familiar with flowchart notation? It's kind of, well, as it says on the tin, really. So we start at the top. Okay, we do all of our initial calculations, initialize the variables, set the boundary conditions, set what our tolerance is, and so on and so forth. Calculate U0. Okay, U0, that 0 should actually be a superscript, but that's our initial conditions. Remember, it does, with elliptic equations, U0 doesn't matter. I just tend to initialize it all at zeros. If you want to do some, initialize them all at 99 if you want to, you'll still get the same answer eventually. Okay, and now we have a decision block. Okay, you've got to check whether the error, when I say error, I mean that's the L2 norm, is the error greater than tolerance? Remember, tolerance is some small number. So before we get to this decision block, we got to specify the error of being a number which is bigger than toll. Okay, so for the first time round, we want error to be bigger than toll. Okay, if it is, we then calculate our next estimate. Okay, UK plus 1. Calculate the L2 norm, which gives us some value. I've called it error, but it's the L2 norm. How far apart are our two estimates? And then lastly, not forgetting, we update our current estimate K with the ones we just improved on. Okay, and then we go around again. Has our error reduced so it's less than toll? If it has, we go to the end and we finish and we've got a solution. If it hasn't, we do it all again and keep going. Okay. Eventually, this will get smaller than toll and we have a reasonable approximation of the solution. Okay, so that's the flowchart. And if you do that for this problem, these are the solutions. So what I'm going to do now is I'm going to fire up MATLAB and I'm going to show you how we build a program to actually calculate these solutions. And it's something which we'll also do next week in the lab sheet. Okay, so all right, so I'm going to fire up MATLAB. So I'm going to call it Laplace. Okay, so what we're going to do is we're going to work the way through the building of this program. Oh dear, I better not call it Laplace.m because it looks like it's already. Oh, it's a Laplace transform. Fair enough. I'll call it Laplace example. Okay, yeah. Okay, so all I'm going to do is write a program which will calculate the solution. So first thing you'll notice I always do is clear the workspaces. It's just a habit I have. Okay, and then we need to define the variables. Okay, so what variables do I need to define? I don't think there are many actually, are there? I know, let's say toll. What should we set as a tolerance? We can change it later, it doesn't matter. What do you want? Some small number. No? Come on, you got to think. I'm not doing all the work. Yeah, that's what I always use, but yeah, we'll use it. Error has to be some number bigger than toll. Give me a number bigger than that. Bingo. Okay, so defining, I call these variables, sort of not really, but yeah. Okay, so tolerance is my small number, error is my 1. What I'm going to have to do now is initialize U. Okay, so U is going to be my matrix. Okay, so I'm going to use the one from the notes. Okay, what I'm going to do here though is I'm going to do it. No, actually, I won't. Normally I flip it upside down, but I won't in this case. Okay, so what we have is we have 5 going across. They're all 8.9s at the top, aren't they? Okay, then we've got 8.4, 0, 0, 0, 9.2. So what I'm doing here is I'm just filling out the starting values for my matrix. 7.2, 0, 0, 0, 9.4. We've got 6.1. Should have made better. Should have made these up to be a bit nicer, but okay. So let's just run this program right now just to check what I've got. Okay, is that working? Looks all right, doesn't it? Yeah, that's fine. Okay, so what I'm going to do is I'm going to use a while loop. I'm going to use a while loop because we don't know when we're finished. We don't know when we'll reach convergence. Okay, if I use the for loop, I'd have to say when I'm going to finish the loop. We don't know, so I'm going to use a while loop. Okay, so I'm going to say while the error is bigger than the tolerance. Okay, so we're going to keep iterating until this error value becomes less than the tolerance. Okay, so first thing I'm going to do is we have 6 nodes which we're solving for. Okay, so if I just go back to the screen, we have these 6 nodes I'm solving for. I need to loop through these nodes, each individual. If I do row by column order, I start on the first row and do column 1, column 2, column 3. Then I move up to the second row and do 1, 2, 3 again. So I need a nested for loops. Now, right at the beginning, the first lab of this year, I got you to do an exercise with the Fibonacci series with a matrix. The reason I did that is because I wanted you to practice nested loops. Okay, so the first loop, the outside loop, is the J loop. Okay, so I'm going to loop through both rows of my computational nodes. Okay, so that's the outside loop. Inside loop is the I loop. Now this loops along the columns. So when J is 1, we go column I goes 1, 2, 3, then J goes up 1, and I goes 1, 2, 3. Okay. Right. What I'm also going to do up here, I know I'm sort of dotting around the program a bit, but I just thought of this. I'm going to use UKP1 as my updated estimate. Now the reason I've initialized it here is because this U contains all of the boundary nodes. So what I've done is by setting UK plus 1 to be equal to U, okay, all the boundary nodes will also be copied across to UK plus 1. Here, I'm not in the boundary nodes. Okay. Actually, I've also noticed a bit of an error. What I need to do is go from J is 2 to 3, and that is 2 to 4. And the reason I've done that is because if J went to 1 to 2, it would have started on this row and then go to this row. I need it to start on this row, going up. So J starts at 2, goes to 3, and I starts at 2, 4, 2, 3, 4. Okay, so that's another thing which I just had to change. Okay, right. So the Jacobi method, UK plus 1, JI, okay, is equal to a quarter. 0.25 times the node to the north, that's J plus 1I. Okay, remember J is the first number J, that's the row number. So the one to the north is going to be J plus 1 plus U, J, I plus 1. That's the node to the east. So I'm going to go north, east, south, west that way. Plus U, J, J minus 1I. That's U, J, I minus 1. Okay, so that's my Jacobi method. What I have to do after that is calculate whatever the error is. Okay, so the error, how have I done it in the... yeah, what we can make use of is the sum command. Okay, so if I say error is the square root and the sum, so I've got a nested sum. Now, why have I got that? What I'm going to do is just show you on a quick dummy matrix. Okay, if I sum A, it sums the columns. Okay, so if I do sum of my matrix A, it's added 3 to 1, giving me 4. Add 2 to 4, it's giving me 6. If I do a sum of that sum, it will add to 4 and the 6 together, give me 10. Now 10 is 1 plus 2 plus 3 plus 4. So if I want to add up all of the elements in an array, that's what I do. Okay, so that's why I've got double sum there. Okay, and now I need the difference between our improved estimate and our old estimate. Okay, and we've got to square that as well, haven't we? Yeah, so if I square that, remember using the dot power. Okay, so that's calculating our L2 norm. Right. Okay, so let's tidy this up a bit. Calculate Jacobi iteration. Let's calculate L2 norm. Okay. One thing I haven't got on this program is a way of recording how many iterations did it take. So I'm going to use an iteration counter. So what I'm going to do is I'm going to say, I'm going to start off k is equal to 0. And whenever I perform an iteration, I'm going to say k equals k plus 1. Okay, so that'll allow me to keep track of the number of iterations I'm using. So I'm going to say update k. And what I also have to update is if I go to the bottom, I have to update u. So u becomes our improved estimate. Right, let's see what we get. If I run this, hopefully it runs without any issues. There we go. It's done its job. It's run. Okay, you can see these are the values in there. Some of them look a bit different from what I've got in the notes. Hopefully they're okay. Oh no, no, it seems to have worked. Okay, so that's performed all those iterations. And if I just see how many iterations it took 34. Okay, for some reason it took 33 in the notes. I don't know quite what happened there, but okay, so it says here it took 34 iterations. So I had to keep improving the values over and over again, 34 times, until we got k down to 34. That doesn't tell us a lot about the convergence behavior. Okay, we're going to see next week why convergence behavior is important. What I'm going to do now is just alter. I'm going to output the current estimates. Okay. I'm going to output current estimates. So I'm going to use nested for loop again, using row by column order. So exactly the same as I've done at the top. Okay, and I'm going to use an fprintf command. And what I'm going to do is I'm going to output then 10.6 decimal places. And the thing I'm going to output is UJI. Oh, actually, I'll output UK plus 1 JI. Okay, so what this is going to do is simply create a row. It's going to create a row of all of these, all of the U values, UK plus 1 value. Okay, after I've completed one row, I'm just going to put an fprintf, and I'm going to put a U line. Okay, that backslash n means okay, I've outputted all one row of my values. Backslash n means okay, we're going to start a new line. Might as well output the k value as well. So the k, I'm going to say, how many iterations am I going to take? It's the k value. Okay. Fingers crossed this works. Yeah, there we go. Oh no, outputted I4. Ah, I've got the percent. 300. Am I outputting the right thing? 4i, yeah. Thank you. There we go. So what you've got here is at the top. I haven't outputted the first ones yet. So if I copy and paste all of that, okay. So if I want to output a row of initial conditions, there we go. They're outputted at the top there. I've forgotten the K, but we started off with zeros. Okay, the first estimate improved each one. Remember, there's row by column order. Okay, and as you can see, as we go down, these start to sort of zoom in. These start to converge to a particular accuracy. What I'm also going to do is output the L2 norm. Just reduce that by about 2. If I output the L2 norm as well, I could do that here, kind of 8%, 8.6F. Let's output the error. Okay, so I'm going to have to go up a bit. Okay, so this on the right, the far right column, this is my L2 norm. This is a measure of how close I'm getting. And we said 10 to the minus 6. Okay, so as you can see, as we improve on the estimates, this gets smaller and smaller. Okay, and then that is just going to dip below the next iteration. Well, actually, it finished on this one. It should have finished on this one. Okay, that's just going to dip below 10 to the minus 6. That stops at 33 iterations. What if we play around with this a bit? Okay, what if I say, okay, I don't really want it that accurate. Let's make it 10 to the minus 3. Run that again. Took 20. So you can see, to converge to 10 to the minus 3, it only took 20 iterations. Okay. What if I want to be ultra accurate? Let's say a billionth. Okay. 40. Actually, that didn't take long. Actually, 47. I was expecting something massive. Okay. Generally speaking, the more nodes you have in your system, the more iterations you require, because each node has an effect on the value of every other node. Okay, remember the whole domain of dependence, range of influence. Okay, so as you up the number of nodes, you significantly increase the number of iterations. Modern computers, that's not a problem. But what if your job takes hours, days to run? Okay, then you've got to consider, okay, we need a faster method. Okay, fortunately, faster methods do exist. Method called Gauss-Seidel, and what SOR methods, which we'll be doing next week. Okay. Right, and there's the Jacobi iterations from the notes. Right, so I'm just going to stop the recording there.